So today I'm going to talk about work on chiral gauge theory. I want to start with a very memorable conversation I had with Pierre Ramon, who described giving a colloquium at Tallahassee while Dirac was still alive. And a conversation with Dirac afterwards revealed that Dirac thought his whole life's work was pretty much a failure because quantum field theory had infinities that no one had learned how to deal with. This seems like a sort of quaint and sad point of view from the modern perspective. We've been sort of all trained or have absorbed the Wilsonian picture that, first of all, addressing the question, how do you compute something in a quantum field theory, really compute it, you have to have a UV completion, but we can lie as much as we want pretty much about the UV in order to make the calculation easy, because these theories fall into universality classes and there's no need to have the true UV in your computation so long as you're in the right universality class. So then the task becomes, if you want to find out what's in the UV, which most of us do, that's why we're physicists, we want to understand the theory all the way down to the base, we have to scrutinize irrelevant operators to try to distinguish between theories in the same universality class, such as trying to find out whether the neutrino has a Majorana mass or not. And this sort of was the effective field theory revolution in the sense that effective field theory now was sort of a controversial or disparaged idea maybe in the 70s and 80s, and now it just permeates everything in the literature. But there seem to be some clues about the UV that do not come from irrelevant operators. One of them was found in the 50s. Landau, I believe, pretty much forbade work on quantum field theory among particle theorists in the Soviet Union after he discovered the Landau pole. He thought that QED had this terrible disease in it. And it was saved, however, by the discovery of asymptotic freedom. And there are related issues that come from setting the RG from the low energy theory that tell us something about the UV that does not have to do with irrelevant operators. One of them is whether, people setting vacuum stability in the standard model, or studying coupling constant unification. All of these provide interesting clues about the UV that don't come from irrelevant operators. The other one is the chiral anomaly. Anomalies are a very interesting and phenomenon that depends on the UV, because UV is required to break symmetries that the IR theory doesn't break. I mean, we say that the UN axial is not a symmetry of QCD, but that really relies on the fact that UV physics breaks the UN axial physics. It's not QCD itself. Yes, FF dual gives us a winding number. There are zero modes in the winding number, but the connection between the winding number and the fermions only comes from the UV theory. So an interesting question is, how can the chiral anomaly be achieved in a computable theory, one that Wilson would recognize and put on a computer, and how can this be achieved without the laws? What is the correct UV completion? How do we have a Hamiltonian that really makes sense in a completely computable theory that correctly reproduces the anomaly? And in the process of trying to answer these questions, can we learn something new about the standard model, in particular about its UV properties? So in this talk, I'm going to focus on lattice theories, which are sort of the quintessential computable quantum field theory, with both global and gauged chiral symmetries, and it'll take me to discussing edge states and topological phases, how to see Weyl fermions on a lattice, and getting around the Nielsen-Ninomiya theorem, how you might gauge the theory, an interesting issue about U1 symmetries and unusual 't Hooft operators that was brought up by Martin Golterman and Yigal Shamir recently, and then a suggestion that one could come up with a description of QCD without a strong CP problem. And then just in the conclusions, I'll mention the challenge of trying to construct a Minkowski version of such a theory, and which I believe is a necessary step if you want to actually understand what is the true UV physics above the standard model and not just a convenient fiction. So anomalies, the heuristic picture for anomalies one sees that is useful for teaching students in a quantum field theory class. You just look at the Dirac cone here in 1+1 dimensions. You turn on an electric field. Charge comes out of the vacuum for the right-handed modes, goes into the vacuum for the left-handed modes. And this infinite source and sink for fermions allows chiral symmetry to be violated while total charge is not violated. This requires the Hilbert hotel. You've got an infinite hotel loaded up with electrons, and you can always take as many out or put as many in as you want because all the people in the hotel just have to move over by one. This cannot exist for a lattice which has a finite number of degrees of freedom. And what's sort of shocking to me is that there doesn't even exist a perturbative regulator for chiral gauge theories in Minkowski spacetime that's known to work beyond two loops. The dimensional regularization, has this sort of kludge designed with gamma 5 where it anti-commutes with gamma matrices in 4 or less dimensions and it commutes with greater than 4. But I'm not an expert in high orders of perturbation theory, but I talked to Collins and he said he did not know of any proof at all that this thing works beyond two loops. And we know that other things like Pauli-Villars don't work for non-abelian gauge theories and so on. With a finite number of degrees of freedom on the lattice, if chiral symmetry is broken by anomalies in the continuum, it must be broken on the lattice. But then there's a big question. If you break chiral symmetry of the lattice, is there a way to do it that still permits chiral gauge theory? So I'll start with just a quick mention of the Nielsen-Ninomiya theorem. If you consider a Euclidean fermion on the lattice with some sort of operator written in momentum space, which is integrated here over the Brouillard zone, what you want is a massless Dirac fermion with chiral symmetry, and really Nielsen-Ninomiya isolated 4 properties that would be desirable. One is that D is periodic and analytic, which is in momentum space, which gives you locality and position space. The next is that you want to have the theory look like a Dirac fermion when the lattice spacing gets small. You want the derivative to be you want the fermion operator to be invertible everywhere in Euclidean spacetime except for at p equals 0, so that there are no doublers, no light states that survive the continuum limit except for at p equals 0. And lastly, you want to have some chiral symmetry, some matrix that anti-commutes with D. And the Nielsen-Ninomiya theorem says that you can have at most 3 of these 4 desired attributes. And so the question is, if you want to have number 4, which seems to be required to project out a Weyl fermion from a massless Dirac fermion, what would you sacrifice? Or is it in fact true that you need 4? Now, chiral edge states appear quite naturally in nature in actual lattices, namely, if you look at the integer quantum Hall effect, a cartoon for what's going on, is you've got your Landau levels here, but the edges cut into the Landau levels, and you see fermions hopping in one direction on one edge and down the other direction in the other edge. So you've got chiral fermions here, and if I apply an electric field, which these look like left and right-handed 1+1 dimensional fermions with gapped states in between. When you apply an electric field, you should have an anomaly, and that anomaly is just accounted for by the Hall current, which varies charges across from one wall to another. So it's not like you have an infinite Hilbert hotel. You've just got a Marriott and a Hilton and a shuttle bus that goes between them, and when you have too many people in the Hilton, you send them over to the Marriott. So the analog exists for Dirac fermions too. It was discovered in the mid-70s by Jakiv and Rebbe that if you have a Dirac fermion with a space-dependent mass, and here I show one in 5 dimensions with a mass profile in the extra dimension, that this theory has, you can do separation of variables where you have 4-dimensional spinners and a 5th dimension function of x5. And you find that where this is an eigenstate of chirality, you find solutions which depend exponentially on the mass. And one of these is normalizable. And if you have a domain wall type structure for the mass, it's localized. at x5 equals 0, but it only occurs for one of the chiralities because the other chirality solution is delocalized, not normalizable, and has to be thrown out of the system for if you want to consider a Hilbert space. And furthermore, if you have a wall and an anti-wall, then, or if you just have a wall, then what Callan and Harvey showed is that when you integrate out the mass of bulk fermions, you generate a Chern-Simons term, and the current on the Chern-Simons term actually accounts for the currents that go on and off the wall to account for the anomaly properly on the boundary. And in fact, the current is quantized, the conductivity is quantized in units of E over H, which can be recognized as the conductivity from the von Klitzing discovery. Except for particle theorists say that H is just 1 over 2 pi, and so if they set E to 1, and so they may not notice that what they have. So an interesting question, which wasn't asked really in the 70s, was why does the Dirac equation have a massless state? It looks like it just arises as a solution, but is there some deeper reason? And we know now from condensed matter physics that in fact there's a deep reason. A quantum field theory with a free massive Dirac fermion in odd space-time dimension can be in 2 different topological phases depending on the sign of the mass, or more different phases if there's more complicated UV physics. And the domain wall is the boundary between these 2 topological phases where the mass is positive on one side and negative on the other. And the only way to connect 2 topological phases together physically is if the theory goes gapless at the junction, and that's why there's a massless fermion there. So what's interesting is that there's nothing in this construction that is a problem for the lattice, because it's a construction in 5 dimensions where there's no chiral symmetry. You don't have to deal with the Nielsen-Ninomiya theorem. You just put Wilson fermions on a 5-dimensional lattice with a space-dependent mass. You find 0 modes on the boundary, and you also find Hall currents between the 2 boundaries. And furthermore, you can show that the coefficient of the current is quantized with just the right coefficient to account for the anomaly for the whatever 0 modes you find on the walls. And this is known in condensed matter physics as the bulk boundary correspondence. So no fine-tuning, an ordinary hotel. The 5th dimension provides explicit chiral symmetry breaking because there is no chirality in 5th dimension. That accounts for the anomaly that would but otherwise, what's the nice feature of this is that it's the only chiral symmetry breaking in the theory that you see in the IR, just the anomaly. In particular, you have multiplicative mass renormalization and other features if you try to formulate, say, QED on the boundary. So the picture is of Wilson fermions on the lattice now. Looks like this. This is the gauge coupling on the vertical axis. This is the ratio of the mass to the Wilson coupling on the horizontal axis. The traditional place to tune for a continuum version of QCD is right to that point, to the 2nd order phase transition there. But you also find inside these yellow regions are topological phases, and those are the phases where the boundary theory would have chiral fermions. So this is used to implement QCD when you have need for good chiral symmetry, such as if you want to look at weak matrix elements. You don't want horrible mixing of operators between different chiral sectors. This is the formulation that's due to Shamir, which is on a finite slab where you've got periodic boundary conditions on 2 boundaries, if this is a 1 + 1 dimensional theory, and you've got your 1 + 1 dimensional edges here where the chiral fermions live. So the lattice looks like a cylinder. Periodic boundary condition goes around here, and these are the 2 edges where your chiral fermions live. So this is a theory with almost massless right and left-handed fermions. However, there is a small wave function overlap if you're at finite volume, which goes like e to the minus 2 ml, where m is the mass of the fermion in the bulk, and L is the distance between the walls. Now, an interesting question is, well, if you think effective field theory, you'd say, well, okay, forget the bulk fermions, let's just look at the edge states. Now you've got chiral fermions on a lower dimension lattice. Why don't you run into the same problem that Nielsen-Ninomiya were worried about, namely that you've got to have a periodic dispersion relation because it's on a lattice. And yes, you've got your pole at p equals 0 for your massless state, but don't you also have to have a pole at the edge of the Brouwer zone because the lattice on the edge is periodic? And the answer is no, because in fact, on the lattice, you get an exponential fall off in the extra dimension that depends not on the bulk mass, but on m effective, which depends both on the bulk mass and on the Wilson term. And the Wilson term cares about the momentum of the state moving along the edge. So in fact, when you reach a critical momentum, which is less than pi over a, the state gets broader and broader and delocalizes and becomes a 5-dimensional state before you ever reach the edge of the 4-dimensional Brouwer zone. So UV physics is coming in now as 5-dimensional physics. It intervenes before you could see the problem that is imposed by periodicity. So when you look at the spectrum of a system like this, you see a whole bunch of bulk. So this is energy versus momentum. You see a whole bunch of bulk states, which are gapped. And then you see a chiral mode that comes across here. You have the Dirac cone, but then this right-handed mode goes off the Brouwer zone, repeats periodically, comes here, and becomes the left-handed one coming back, repeats, and so on. So it sort of forms a figure 8 on the Brouwer zone. So the question then is, could this be used? This is used for simulating vector-like theories with chiral symmetry, but could it be used for, with approximate, because you're working at a finite volume, approximate global chiral symmetry, but could it be used for formulating chiral gauge theories on the lattice? It doesn't look promising because the chiral symmetry is approximate. But the answer is maybe, and it's a series of steps that were taken in the 90s. The first was to take the infinite extra dimension limit to obtain chiral symmetry. If the walls are infinitely far apart, then you have exact chiral symmetry. This doesn't look like it'll be useful for doing an actual simulation, however, because of infinite volume. But then Neuberger derived the effective 4-dimensional fermion operator on the edge by integrating out the bulk modes and came up with what's called the overlap operator. And this overlap operator, you know from the 5-dimensional theory, has to have very good chiral symmetry because the chiral modes can't talk to each other. So what is this operator? And how is chiral symmetry realized? Because it also has the anomaly built into it. Well, Lucia realized shortly afterwards that this operator obeyed an exact type of chiral symmetry, but not the usual anti-commutative gamma 5 equals 0, but rather something that goes to 0 in the lattice spacing 0 limit. And this is called the Ginzburg-Wilson equation, which was derived years before, but it was abandoned because nobody had a solution to it. Nobody knew what D would obey this equation. And Lucia showed that this implies an existence of a chiral symmetry that has a bizarre property in Euclidean spacetime that while psi transforms normally, psi bar has something that's slightly non-local in its transformation. And this combination of symmetries is an exact symmetry of the lattice action, while at the same time, it's not a symmetry of the lattice integration measure. So you get a situation that looks very much like the continuum. You have an exact symmetry of the action. You have the measure breaking it, and the way it breaks it is by exactly the right amount to account for the anomaly. Namely, it's the fermion index. So that's still a vector-like theory, but what Lucia proposed then is to use the symmetry to project out Weyl fermions from the overlap operator. And that can only work when the anomalies cancel in the gauge measure, which is good. That's a necessary condition, but he was not able to construct the fermion measure for non-abelian theories, which is a problem. And furthermore, the theory it cannot be continued into Minkowski, sorry, that's garbled, into Minkowski spacetime because there's no Hamiltonian formulation for the overlap operator. And in fact, there's a theorem that there shouldn't be by Minkowski and Senke. And so there's no Hamiltonian for the overlap operator. And the symmetry projection requires unrelated transformations for psi and psi star, which can't be realized in Minkowski spacetime. So, you might say, well, why do I care? Isn't a computational tool for Euclidean Green's functions enough? And I would say no, because we know that a Chiral gauge theory has got a sign problem that will be exponentially difficult on an ordinary computer. So if you want to compute, you probably are going to have to figure out how to come up with a Hamiltonian approach and put it on a quantum computer someday. Furthermore, if only a scheme that works in Minkowski space actually can shed light on the question we're most interested in, which is what's beyond the standard model. So instead, you can consider a more physical approach, which keeps the fifth dimension and asks, well, what about edge states on a manifold with a single boundary? So if you look at fermions on a disk in the continuum first, with, say, an infinite negative mass on the outside and a finite positive mass on the inside, shouldn't this have a Weyl fermion on its edge state? I mean, after all, we know there should be some sort of state on the edge, and it's not going to turn around as it goes, so isn't an exactly Weyl fermion and massless? And can this be realized with Wilson fermions in the lattice then? Well, I had all sorts of reasons I won't bore you with why this couldn't work, and so I didn't think about it for about 30 years. But then I decided in a moment of boredom to just calculate it, and it turns out the theory does have Weyl fermions on the edge. There's an exact Weyl mode circulating the disk in only one direction, even at finite size. You don't have to go to infinite volume. The Chiral symmetry is exact. It's part of the exact U1 fermion number symmetry of the original theory. And the total angular momentum variable of the fermion plays the role of linear momentum on the disk edge, and it's quantized. So you actually don't have a zero mode here. It starts off at j equals a half. If you consider an annulus with a small hole in the center with radius r prime, then the mirror fermion lives on the inner boundary, and it's got momentum j over r prime with the opposite direction. And furthermore, the same physics works on the lattice. The physics looks sort of like the continuum annulus, where the inner radius corresponds to the size of lattice holes, lattice spacing A. And thus the mirror states do not have a continuous spectrum as the outer radius gets large, which invalidates the assumption Nielsen-Ninomiya, which is that in the large volume limit, the spectrum becomes continuous and analytic. So you put this on a lattice, and we did it on a roughly circular lattice here, shown here, and you look at the spectrum, and this is what you get. The vertical axis is the energy for the energy eigenstates, and the horizontal axis is the expectation value of the angular momentum operator. Okay, and this magenta line there is not a fit to the data. It's the exact minus j over r plot. And so you see, this looks very much like a Weyl fermion dispersion relation here, since J plays the role of the momentum around the edge. And the return mode, which Nielsen and Ninomiya said we should expect, does not exist. It's somewhere up in this tornado as a bunch of discrete dots. In fact, if you look at a particular mode here, you see that the charge density is localized completely on the outer boundary, and the current is also localized on the boundary and is only going in one direction. If you look at a different mode off of the Weyl line, you find something very different. It's a completely delocalized mode and has no obvious chirality. It's rotating in both directions in different places. So the last question is, how would you gauge this theory? Okay, so the gauge fields have to couple to the fermions. The fermions are 5D, so the gauge fields have to exist in the bulk. They can't be just living on the boundary. Otherwise, you break gauge invariance. But furthermore, there's a problem, though. 5D dynamical gauge fields would be expected to have a trivial continuum limit, because gauge coupling is an irrelevant operator in 5 dimensions. And you need non-trivial gauge fields to propagate, but only on the 4D boundary. So a suggestion that I proposed is that you look at, and it's not clear that there's a Minkowski analog to this, I'll get back to that. You generate stochastic 4D gauge fields on the boundary. You then continue them into the bulk as a solution of the classical Yang-Mills equations with that stochastic field as the 4D boundary condition. You then do your accept-reject of your stochastic field based on the 4D Yang-Mills action times the 5D fermion determinant. Because the 5D fermions see the gauge field throughout the bulk. This sounds like a horribly non-local thing, because after all, these 5D fermions are seeing this 5D gauge field. The 5D gauge field is related to the 4D gauge field via Green's functions, classical Green's functions, and it's extremely non-local. However, you can show that all of the operators you generate, if you expand the 5D fermion determinant into e to the sum of operators, that the one that is the important one is the Chern-Simons operator, and it exactly accounts for the anomaly on and off of the boundary, and the other stuff is irrelevant. So the desirable features are that the 5D fermion determinant will be irrelevant, but only so long as the 4D gauge anomalies cancel. So this has a feature that we'd like to see, which is you want to know, if you have a formulation for a 4D chiral gauge theory, you want to see how it goes wrong when the anomalies don't cancel, and the answer is it doesn't look like a 4D theory. It looks like a strange non-local 5D thing. There is a strange feature, though, because since instantons are solutions to the classical equations of motion, they can propagate into the bulk, even though other features of the gauge field damp out in Euclidean spacetime. Furthermore, expected fermion zero modes in the outer boundary are accompanied by mirror zero modes in the bulk, as was emphasized by Goldman and Shamir recently. So the picture is, and in particular, there's a strange unwanted U1 symmetry. So the idea is that if you have a massive Dirac fermion on the bulk giving rise to a chiral fermion on the boundary, for every boundary Weyl fermion, you have one massive Dirac fermion in the bulk. There's an exact U1 symmetry for each bulk fermion. It's just fermion number in 5D. And this leads to too much symmetry for the boundary theory. Because, for example, if you had n flavor equals 1 QCD, you need two Weyl fermions, for a left and right-handed quark, which means two bulk fermions, which means a U1 cross U1 symmetry. So this looks very weird, because it says you have an exact vector symmetry and you have an exact axial symmetry. But the exact U1 symmetries were the basis for the bulk boundary correspondence. It's how you show that the Chern-Simons current that you generate cancels the anomaly on the boundary. That was the Callan-Harvey argument. So where does the exact U1 symmetry become a problem? And the answer is that when Callan and Harvey did their calculation, they assumed that all the bulk modes were gapped. Well, when you have an instanton, you'll find that the boundary gauge, with the boundary gauge field as non-trivial topology, there can be a zero mode in the bulk. So here is the instanton on the outer boundary, and it's got a fermion zero mode on the boundary if your boundary quarks are massless. That instanton gets continued into the bulk, and if you tell me the winding number of the boundary field is 1, then this thing can't come out as an anti-instanton anywhere. It has to end somewhere in the bulk, and where it does, there'll be a fermion zero mode. So suppose the boundary theory is QCD. Even when boundary quarks have mass, these configurations, however, won't contribute to the vacuum since there are exact bulk zero modes. So the zero modes in the center here will make these types of configurations not contribute to the partition function. So instead, you'll just get these things where the instanton is correlated with an anti-instanton on the boundary. There will be no singular gauge fields in the interior, no bulk zero modes. So if the bulk zero modes kill the contributions to the vacuum with nu not equal to 0, the boundary theory vacuum looks like conventional QCD, even though it has massive boundary fermions, but restricted to winding number equals 0. And that you can show is equivalent to theta equals 0 up to 1 over volume corrections. Because you can always impose nu equals 0 by integrating over theta. The vacuum energy depends on theta, so you have, in Euclidean spacetime, that means you have an e to the minus volume cosine theta type times m quark contribution to the partition functions. When you integrate over theta, a saddle point approximation tells you that theta is highly localized around 0. So here's a bizarre world where we live out here with massive quarks, and unbeknownst to us, the gauge field configurations that would give rise to physical CP violation are canceled because zero modes appear in the bulk in the fifth dimension and kill those configurations. Furthermore, it looks like a strong CP problem solution. The thing that's interesting, the eta prime in the boundary world is massive despite an exact U1 axial symmetry. How is that possible? Well, the 't Hooft operator you get ends up looking like this. This is exactly what you would get if you restrict it to ordinary QCD to nu equals 0. This is a theory which, if you expand it to second order beta prime, you find it gives rise to a massive eta prime. But it also has an exact shift symmetry. The zero mode, the 4 momentum equals 0 mode of the eta prime does not get a mass. It has an exact shift symmetry. So this weird non-locality that you get when you restrict to nu equals 0, both has an exact U1 axial symmetry and a massive eta prime, and there is no theta problem. And it's equivalent to theta equals 0 QCD with up to 1 over volume corrections. Still, there are exotic nu not equal 0  't Hooft interactions. If you simulate the standard model this way, you'll still have proton decay, but it requires an 't Hooft operator that transfers baryon and lepton number in and out of the 5th dimension. So the 't Hooft operator has these zero modes that exist in the extra dimension. It won't give the standard rate, I don't think. So it's not in the same universality class, but it is. So the question is this irregular for the standard model, or is this regulated beyond the standard model of physics? And I'd say the line is a little bit blurred here. So I want to say that this is sort of an interesting picture. It's a very physical view for how chiral fermions appear. It's very natural having an extra dimension giving rise to chiral fermions. An extra dimension could be a natural UV completion for anomalies with the described construction, and 4D theories really only can emerge if the 4D gauge anomalies cancel. And from work by Witten and Yonokura, it's not just the 4D gauge anomalies, but also discrete perturbative anomalies that have to cancel if you want to decouple from the extra dimension. The Nielsen-Ninomiya theorem, however, is no longer an obstacle. What appears in this theory is not purely 4D when gauge topology is non-trivial. We can call this the eta prime portal to new physics. If gauge anomalies cancel, it appears that the chiral gauge theory can be regulated, giving a theta equals 0 theory in large volume if bulk fermion zero modes are exact. But it still falls short of of the admonition I started with, which is we'd like to have a Minkowski formulation so that we actually understand what the real UV physics might look like. Is it possible to have a Minkowski formulation of 5D gauge fields where the gauge bosons only actually propagate on the 4D surface and look gapped or constrained or something off the 4D surface? It's not at all obvious. It's an interesting direction I still want to explore. Thank you.
Yeah, thanks. Very interesting talk. Yeah.
How does the usual argument the cluster decomposition argument go wrong?
So the argument that I gave about nu equals 0 being equivalent to theta equals 0 with 1 over volume corrections, I think is accurate. The 1 over volume corrections are nasty non-local stuff, but they do go away in the large volume limit. The exotic 't Hooft interactions that involve zero modes in the bulk, I don't know how that connects. There's also the issue that Seiberg's raised. He wrote a paper with, I believe, Banks and Dine in the early 90s called the irrational axion. They looked at a theory where there were the same axion operated with two different gauge anomalies. And the high energy gauge anomaly sort of fixed the potential for the axion, but left the 2 pi n type of shift symmetry. And then the lower gauge theory, the axion coupled with an irrational charge. Okay, it's sort of a hideous model, but the point was then that you could always get as close as you wanted to the minimum of the second gauge group's energy potential by doing enough integer jumps because of the irrational charge. This theory, however, has a landscape which is hideous. I mean, it's basically not compact, and it's truly hideous because you have to go very far in field space to actually find the true local minimum with many barriers in between. So in terms of an evolutionary theory, this theory would get stuck in the wrong vacuum. Okay. He came up with a different theory around 2010 or something, which used a slightly different mechanism, and again concluded that in Minkowski spacetime, if you try to fix topology, you end up with a theory that can be UV completed in a way that's consistent with cluster decomposition, but has a problem which has a complex ground state where you won't find the true minimum. So what the connection is between these things, I'm not completely clear.
Yeah, this was a little complicated for me, but I have a question. Can something similar be done, say, in 1+1 dimensions, say, for a billion theory?
Yeah, definitely can be done 1+1 dimension. It's a little bit different because you don't have, so U1 and 1+1 has non-trivial topology and zero modes and everything, but they aren't localized like instantons, right? It's the E field wrapping around, so I don't know quite how to visualize the same picture that I've developed with an instanton gas model. But yeah, I presume it can be. I haven't thought.
Yeah, it would be interesting, say, like a Schwinger model with chiral.
I think these models where you set it up to simulate QCD on the boundary, where you don't expect a sign problem, and study the topology would be quite interesting, yeah.
Okay, thanks. Yeah.
So normally if you have a constant shift symmetry, there's also configurations that are close to constant, very slowly varying, that give you massless particles.
I'm sorry, I missed that.
If you normally have a shift symmetry, like the eta prime shift symmetry, then nearby there are almost constant shifts.
No. No.
So is that what breaks down? This is what breaks down here, is that there are no closely related, almost constant shifts. That's how you avoid Goldstone's theorem.
It's a discontinuous spectrum exactly at p equals 0.
Okay.
So I just wanted to ask about the connection back to Minkowski space. So is the thing you're worrying about the sign problem in the Pfaffian, or is it some other like Osterwalder-Schrader kind of breakdown? The
sign problem in chiral gauge theories?
Is that the thing that you're worried about going back to Minkowski space, or is there some other Osterwalder-Schrader breakdown?
No, it's the Fermion-Pfaffian, yeah. And I have a physical argument for why there must be such a thing, which is if you consider SO10, say, two different theories. One is a left-handed 16 plus 16 bar, which is a vector-like theory. And the other is a left-handed 16 plus 16, which is a chiral gauge theory. I chose an SO group because they don't have gauge anomalies, so they're both fine theories. Now, in one, you have bilinear condensation, no doubt. In the other, you have to go to a 4 Fermion condensate. So the free energy, the vacuum energy, will be completely different, okay? And therefore, the partition functions will differ exponentially. And the only way they can differ is through the phase of the Pfaffian. So the phase of the Pfaffian must be very important, must lead to an exponentially difficult problem.
So can I clarify that your picture that you are describing requires just one surface instead of the usual two that we have in domain wall? Does it mean that we have to put this 5-dimensional system into an S5, so it's not a torus but a sphere that you can actually
cut out? It could be a 5, so to see the chiral modes, you don't need to have Lorentz symmetry in the low energy theory, so you could put it on a square, on a cubic lattice with open boundary conditions and on all edges. It just has to look topologically like a sphere. But of course, that won't be useful for describing 4-dimensional physics because you'll have this horrible non-Lorentz invariant type of spectrum. If you wanted to look Lorentz invariant, you could either do it on a cylinder where one dimension is treated differently than the others, with where you compact a disk in 2 of the dimensions and everything else is periodic, or you could do it on a sphere. neither of them are very nice
Well,
solutions numerically.
Unless Rich steps up and does his construction, I don't think we can do it on a sphere yet.
Yeah, numerically, they'll be pretty ugly to put it on a square lattice on a sphere. Yes.
Yeah.
I'm not sure I understood the definition of how the gauge fields go into the bulk. So I think at some point you said that you don't want them to be quantum mechanical in the bulk, and I didn't understand why.
So, so the question is why I don't want dynamical gauge fields?
Yeah, why don't you want dynamical gauge fields in the bulk? Yeah.
So first of all, typically when you try to, if you just tried to study 5D Yang-Mills on a lattice, you wouldn't find a continuum limit. There's no second order phase transition. So that's a problem. I mean, from the old-fashioned quantum field theory point of view, the gauge coupling has dimension 1/square root of mass. It's not a renormalizable coupling. You don't expect a continuum theory. Another reason, though, is you want to have, suppose you did this with a U1, you want to have a normal 4D Coulomb law. You don't want them wandering off an extra dimension. And then the last thing is, if there are massless modes in there, you don't really want to see them.
I see.
So, these may be misguided pictures of what's going on, but that is, I don't really see how you get something that looks like a 4D gauge theory if you start off with 5D dynamical gauge theory.
I mean, I see what you're saying, but if I were to try to think about this as a proposal for some BSM physics, it would be quite weird to say that the physics, some of the physics in the fifth dimension is somehow not quantum mechanical.
Well, you can actually do it in a path integral with a delta function constraint in it, where you enforce the equations of motion in the bulk, and you don't put in a 5D Yang-Mills theory, Yang-Mills action, just put the 4D one on the boundary. That's a perfectly well-defined path integral, as far as I can tell, and you can put in auxiliary fields to turn the delta function into auxiliary fields in the action and everything. So the main problem I have with this is that when you go to Minkowski spacetime, the exponential fall off of these gauge modes in the extra dimension in Euclidean spacetime goes like e to the minus p squared times your distance, okay? And so, except for at p equals 0, you'd expect these things to fall off exponentially. But of course, p squared doesn't have to be positive. In Minkowski spacetime, it could be negative or 0, and so that doesn't lead to localization, obviously, very clearly. And obviously, for a U1 theory, plane waves are fine solutions to the equation of motion. They wouldn't have any problem propagating off the wall. So that's why I say I'm a little bit worried about a Minkowski formulation. And I think whether it could be done with, putting curvature in the extra dimension or something that gaps so that when a gauge boson is on shell on the boundary, it's not on shell in the bulk or something like that. I don't know.
So, if I understand correctly, with the current version of your construction, you could go back to your proposal with the rota, right? I mean, you don't really need the circle anymore.
Yeah,
because the mirror fermions
30 minutes didn't give me a chance to talk about this. An earlier version had 2 walls, but the gauge fields die off, so even though there are massless, gapless fermions on the far wall, you don't see them with the gauge fields.
In fact, they help you project onto Q equals 0.
Yeah, I think, I don't know. My hunch is this works better because everything's gapped. And you don't have to worry about massless modes floating around. But I don't have a good argument for it. I can't really describe that model here. We can talk about it.
Okay, well, we're out of time, so let's thank David again. And thanks for